GPS is such a powerful technology, it's natural that we want to use it in our designs. GPS receivers often come in little packages like this. This is the one we're using in our projects in this class. And what it consists of is a GPS antenna, which is this little square thing, and what's underneath there is a GPS processor that's doing all of the signal processing and reception and math that it takes in order to get a good, accurate location from the satellite system. What this device outputs, and what most GPS antenna modules output, is what's called the NMEA, the National Marine Electronics Association 0183 standard format. And what this is, it's an RS-232 compatible serial output that is typically at 9600 baud, but it's often variable. You can make it set to higher or lower speeds if you need to, with an 8-on-1 format. And what you end up seeing from one of these devices is something like this. So this is what's called a log of NMEA sentences. And each of these sentences captures some information about the GPS fix, the GPS antenna's current location, the quality of that signal, and all kinds of other stuff that we might find useful. Let's parse one of these sentences, actually the most important type of sentence that you might want to pay attention to. The one that is most important is the GPGGA. What this entire sentence translates as is first off, you get a preamble, or the prefix. And what this is basically saying, it always starts with a $sign. So a $sign says this is the start of a new sentence. GPGGA is a specific type of message. In this case, it's a global positioning fix sentence. The next thing is the timestamp. So this is the current time this is the current time in UTC, Universal Coordinated Time, as the GPS antenna sees it, has figured out its first time. So this is one of our variables. This is the time in the world, and this is coordinated atomic time, so it doesn't really get much better than that timestamp. Then the next thing you get is the latitude and longitude in degrees on the surface of the Earth. So this next section, in this case, the 4807, the first two or three digits always represents the degrees, and then the remaining digits are the minutes and decimal minutes of a latitude and longitude location. Next, we get the quality of the message. The first number here is the fix quality. If it's 0, there's no fix. If it's 1, it's a good fix. We have enough satellites that we can see and get a position location that's accurate. There's higher numbers that bring in things like DGPS, which is differential, which means that it's able to listen to a ground-based station, which gives it a higher level of accuracy and gives you some more information there. Then there are the next is the number of satellites being tracked, and the horizontal dilution of position, which is basically in meters how accurate it thinks that the specific location is. You basically can think of it as it's plus or minus this many meters that specific location is located. Next, we have the altitude information, both above and relative to sea level. And finally, some specific stuff about different time updates for differential GPS, DGPS, and the checksum data for this specific sentence, which makes sure that no bytes were lost and we can trust whatever the message is. Now, the position is always reported in latitude and longitude. GPS was created as a nautical navigation system, so this was never really intended for personal use as we actually began to use it. It was actually used to help ships navigating at sea so that people wouldn't get lost. And before that, it was a military technology, again, used by the Navy primarily. So coordinates at navigating at sea are represented by latitude and longitude. So what we have here is we have degrees north and south and degrees east and west. And you can remember probably from high school, latitude is flat, so latitude moves the lines of latitude run east to west, and the degrees run north to south. So you can think of the latitude as sort of the y coordinate on the global reference frame. Longitude degrees run east to west, and they go up and down. So 1 degree, a specific location of longitude, runs up and down, north to south along the surface of the Earth, and degrees increase to the west, or actually the decrease to the west. So our west is actually negative in our coordinate. You can think of the longitude as sort of the x-coordinate of our Earth reference frame. So let's work with some latitudes and longitudes. Say we get a sentence and it has this value in it. This is our latitude. It's 48 degrees, 7.038 minutes north. Then we get another number. This is our longitude, and it is 11 degrees, 31.0 minutes east. The degrees and minutes thing isn't super useful to us. It's better if we can represent, it's easier for us if we can represent this in what's called decimal degrees. So in this case, 1 degree has 60 minutes in it, which is a weird thing, but that's the way it works. So we have to divide each of the minutes by 60 in order to get decimal degrees. So we do that very thing, and that gives us a latitude and longitude that now we can basically treat as x and y coordinates on the surface of the Earth. Note that if we get a west longitude, that makes the degrees if we get a west longitude, that makes the degrees basically negative, because the 0 point is Greenwich the Greenwich longitude on the equator. So if we're going west of Greenwich, that is negative. If we're going east of Greenwich, that is positive. So we're here in North America, all of our GPS coordinates, the longitude is going to be a negative number. Now, to use these in our projects, the most important thing that we want to do is figure out our bearing, or where we want to go from where we are, which direction we want to go from wherever we currently are. Often we'll have a source location, our initial x and y coordinates, or longitude and latitude coordinates, and we have a destination that we want to get to figure out which direction, what heading we need to go to find that location. We have to figure out what our bearing angle is. Bearing angle is the angle which is our clockwise from north that will take us, if we follow that heading, to our location on the surface of the Earth. To calculate this, we basically take each of our latitude and longitude coordinates as x and y values, and we can basically do SOHCAHTOA here, right? If I've got my latitude, which is my y coordinate, I know what the difference between my current latitude and my destination latitude is, and I also know what the difference between my current longitude and my destination longitude is. So once I know those two things, you can see that this is a triangle. I don't know exactly what the distance is. I could probably calculate that out, but it's easier since I just have these two differences in latitudes and longitudes. I can just do, what is it, SOHCAHTOA. I've got my opposite and I've got my adjacent. I'll use inverse tangent to get my angle, the heading that I need to go to, my bearing angle that I need to reach in order to reach my destination. Now the challenge here is that in the standard library for our code, the inverse tangent is it takes only one parameter, and that is the difference in y over the difference in x. Now that works great if we're working in between -90 and +90. So if we're in the if the x coordinate is positive in our reference frame, right? So if we're over here, we do that. But if both of them are negative, we end up with getting the same angle that's mirrored across it. So what we can do is we can use the atan2 operation, and it takes the y and x, and based on the relationship between these, it figures out if this is a angle in the first coordinate, or if it's an angle in either the second or third coordinates rather than the first and fourth coordinates. The idea here is that we know our current heading, right? So our car, based on the magnetometer, knows which direction it's currently pointing. Now we have our bearing, which is the location that we want to go, right? So we need to make these two agree. So as you're thinking about how you design your code, think about, given my bearing, my destination heading, how am I going to choose how to turn the wheels so that my bearing and my heading eventually line up and I can shoot towards my destination just by driving forward.